All right, recorder's on, and we are good to go. All right, okay. So today's recording is for both the Tuesday, Thursday class and also the Monday, Wednesday class because yesterday there was a power outage right in the middle of the Tuesday version of this class. And to the dismay of my students, I did not let them go. I go like, there's enough oxygen supply in the room for at least another hour or so. And then the lecture period ended, and then go like, well, I think there's still enough oxygen supply, so we're going to convert the lab into a lecture. So I just continued using the whiteboard and the available light from the windows to teach the class. Until at some point, it's not so much the oxygen ran out, it's the temperature of the room got to the point where it's not comfortable for a class. So that is when I ended the class. But the recording didn't work because the recording requires a bunch of stuff that is on AC power, and so when the AC power was out, I could not continue the recording. All right. Um, all right. So we're gonna do what we're doing today is okay. So I'm gonna show you what it is based on, so that you know what module you're supposed to read to get this content. So we are done with base conversion. Okay, so base conversion is here. And we are moving on to binary addition and subtraction. So that's what this particular lecture is about, is binary addition and subtraction. For those of you who got some time to read ahead, that's actually really good because there are a lot of notations involved in this particular module. And being able to read ahead and just kind of jot down some notes really helps to understand, oh, okay, this symbol means this, or that symbol means that, and so on. But I'm going to explain everything without the assumption that people have read the modules. It's just that having read the modules ahead of time will make everything quite a bit easier in today's lecture. So the format of today's lecture is a little bit different from the earlier ones because I'm just going to give you some live demonstrations that are consistent with the reading content, the reading material, but it is just a presentation that is kind of more of a example-driven way of explaining things. And you'll understand why I would do it this way, as we get into the material. So we'll start with, a calculation of 726 plus 278, like so. So this is a base 10 addition, multi-digit addition. So let me ask, do you know how to do this on a piece of paper? Okay, some of you can probably do the mental math and go like, oh, okay, I know the answer right away. That's great. I don't need that level of competency. I just need to make sure that you can do this on a piece of paper. If I give you time and give you a piece of paper, you know how to do it. So is that a fair assumption? Okay. So I'm just going to do it, the usual way that people do it. Okay. 6 plus 8 is 14. 14 cannot be represented by a single base 10 digit, which can only go from 0 to 9. That's why we have the concept of a carry. Okay, the quantity of 14 says, okay, we are greater than or equal to 10. This quantity cannot be represented by a single digit. So we are going to say, hey, the second row of digit or digit one, how about you help me take care of my 10 and I'll take care of the rest of the 14. That is why we have the concept of a carry. Okay, what I cannot represent, I'm asking the next digit and say, hey, what is a 10 for me? It's just a 1 for you. Can you help me take care of that 1? Is that okay? So now we move on to the second column. 2 plus 7 is a 9. 9 plus the 1 here, which is the carry from digit 0, is once again, oh, it is 10. It's greater than or equal to 10. I cannot store that as a single digit anymore. So now what do? We ask the digit next to us, which is digit 2, and say, Hey, how about you help me take care of the 10 and I will take care of the remaining portion, which in this case is just 0. Are we still doing okay so far? Yes? Okay, excellent. So now when we get to the last digit here, or digit 2, kind of the same story. 7 plus 2 is a 9. 9 plus the 1 is a 10. Same deal. Okay, I can take care of the remaining portion, but then I have an overall carry of 1 here. But this is it. Okay, I'm not moving this carry of 1 all the way down here. I'm just leaving that one kind of dangling as a carry. Okay, the reason why that is the case is because in a computer, whatever the number you're adding, the sum needs to have exactly the same number of digits. In other words, if we use 3 digits for the numbers that are being added, then the sum can only use 3 digits only also. Is that okay? So that's the reason why we have the fixed width between the numbers that we're adding and also the result of the summation. Do we have any questions about that portion? Then you guys go like, but then the result is not 1004. It is. That's what this one is. This carry of 1 is a digit 3, which means this one is basically a 1000. So the 1000 here added to the 4 is indeed 1004. So the result is actually properly represented, just not in one single number. It is separated into the sum and also the overall carry over here. Are we doing okay so far? So this little dangling carry, which I just normally casually refer to it as the overall carry, is kind of important in today's lecture. Is that okay? All right. So now I'm going to rewrite exactly the same addition, but in a slightly more spelled out and tedious way. So same thing, 726 plus 278. But this time I'm going to do it in a different way. Okay. So this row here is actually storing all the carry. It's kind of like saying, oh, we have an implicit carry of 0 to digit 0 because there's nothing to the right hand side of digit 0. So this 0, I just put it here. So now what we do is say we ask, what is the single digit sum of 6 plus 8? It is a 4. And then do we have a carry of 1 to the next digit, to digit 1? We do. We put that 1 here. So this 1 is corresponding to this 1. This 0 is corresponding to this 0. What is the single digit sum of 2 plus 7? Okay. And it's also a 9 here. And does 2 plus 7 give me a carry of 1? No. Does 9 plus 1 give me a carry of 1? We put that 1 over here. And then 9 plus 1 is a 0. 4 plus 0 is a 4. 9 plus 1 is also a 0. But 9 plus 1 being 9 plus 1 here is giving me a carry of 1. So this one is the overall carry, which is the same as this one over here. So are we understanding the new way of representing a multi-digit addition that spells everything out in a kind of tedious way? So we're good? All right. So the reason why I have to change the format from something that is kind of convenient and the way we are used to something that is really kind of tedious and seems like it's unnecessarily tedious is because I'm trying to extract the structure of multi-digit addition. That is what I'm trying to do, which is also why what we do in computer science or code development. We're trying to extract the structure of things so that we develop a single way of doing things that can handle all of the cases. Okay, that's abstraction. All right. So instead of saying, this digit versus that digit versus this digit, over and over again, which is really vague and difficult to understand when there are many, many digits on the screen. So what we'll do is we'll have a numbering system. Part of this you know already, which is how we count the digits. So we have digit 0. Okay, this entire column is digit 0. We have digit 1. This is the entire column of digit 1. We have digit 2. This is the entire column of digit 2. And then we have one tiny little thing for digit 3. So this is something that we have talked about already, how we number the digits in a multi-digit thing. So I hope that is okay. Yes? Okay. All right. So now we also need ways to identify the rows. So 728 is called row X. It is one of the value that we have to add. This is row Y, which is the other thing that we are adding. This one is called row Q, and I cannot even remember why I called it row Q, but we'll just call it row Q. This is row K for carry. I know carry starts with a C, but I choose K in this case because I have a different job for the letter C. Okay, so that's why this is K. This is row S for sum. Is that okay? So now we have a system to designate specific digits in a multi-digit addition like this guy here. Okay, what is the name of this guy? It is Q1. Okay, it's Q1. And what about this guy? It is S2. How about the overall carry? It is K3. That's right. Okay, so now everything has a name. Um, so unless you have read this already in my module or you're reading it and you feel very comfortable with the way I explain things, you might want to jot down some notes. Okay, because just because I feel the module is doing a great job explaining things does not mean that you are going to agree. In fact, the majority of people may disagree that my module is easy to read. Okay, I do have some minority people saying, well, this is exactly how I want the material to read like. Great for those people. Okay, but for people who go like, no, this really sucks. The way you write totally sucks. I cannot understand what you're writing. Then you might want to write down some notes as I explain these things in an interactive way, which means I look at people who are not writing any notes and I go like, well, if you are understanding all the material, cool, okay? But if you're not, then you might want to, kind of write down some notes, which is based on your understanding of the material explained in your own way. Okay, that is kind of what I try to promote, okay, which is doesn't mean that you have to write notes. Does it mean that if you're not writing notes in my class, I would dock points? No, but if that ends up costing you a grade, your grade on not passing a class, that's not on me anymore. Okay. All right. So now we want to look at these digits. Okay. So we got X, we got Y, we got Q, we got K, and we got S. Okay. So these are the rows. So the next thing I want to focus on is how do we compute the single digit sum? In other words, these guys over here, how do we compute those? So if R of UV is computing the single digit sum of adding U, which is a single digit in a certain base, and V, which is also a single digit in a certain base, for now, we'll just say we're dealing with base 10 here. So we have a very concrete base to talk about. So in this case, U can only go from 0 to 9 because it is a single digit in base 10. And V is the same way. It can only go from 0 to 9 because it's also a single digit in base 10. So how do I compute the single digit sum of U and V in base 10 in this case? So it helps to go through a few examples, okay? So we can say R of, we'll do the easy ones first. That's just 5, not a problem, because 5 is less than or equal to 10, so the sum of 2 and 3 is the actual single digit sum. But when you have cases where you have 8 plus 7, then you cannot say 15 because I did say single digit. So what is the single digit sum of 8 and 7? It's 5. It is 5. Okay, very good. We'll do one more example. What about 7 and 6? It'll be a 3 because 7 plus 6 is a 13, But since I'm asking only for the single digit, not counting the excess portion, which is taken care of by a carry, so that is only 3. So knowing all of these examples, how do we generalize the actual equation to go here so we can define the R function? There are a few ways to do it. You just have to give me a way or the most obvious way. See, see, this is the reason why I, as a bad student, never read ahead of time, because then the class is going to be boring because I know all these answers already, and I won't be staying awake or paying attention in class whatsoever. That's me because I have ADHD. Okay, but you may not have ADHD. Okay, so the way the study strategy for you may not be the same as what works for me. Yes, give it a shot. U plus V in parentheses mod 10. Yep, that will work. Exactly. So that's going to work. Cool. Not a problem. Good job. So what I'll do next is I'm going to erase this portion here, which are really just examples, and then we'll go back and say, what about C of UV? In other words, when we add U and V as single digits in base 10, do we end up with a carry of 1, or do we end up with a carry of 0? Okay, so how would you write the carry function? We want C, okay, so give you some examples, right? 2, 3 is going to be a 0 because 2 plus 3 does not create a carry of 1. C of what we already have here, 6, 8 is going to be a 1 because 6 plus 8 is greater than or equal to 10, and therefore we end up with a carry of 1. C of 9, 1 is also going to be a 1 because 9 plus 1 is 10, which is greater than or equal to 10, and that's why we end up with a carry of 1. I have just spelled out the actual expression, just not in symbols. Go ahead, give it a shot. hmm Okay, all right. So if u plus v is greater than or equal to 10, then 1, else 0. Okay, very good. So you might notice that I'm writing if, then, else in a very kind of narrow font. That's for a reason. Because instead of using if, then, else, I can use a C++ expression to do exactly the same thing. It is called the ternary operator. The ternary operator is essentially replacing the then with a question mark. Nope, this part is a question mark. You got it. The colon has something to do with this, but it is replacing the else. The if actually has no representation, so this is taken out entirely. So this is called a ternary expression. What is to the left-hand side of the question mark is a condition to evaluate, just like a condition of a conditional statement. What is between the question mark and the colon is called the then expression. It is the expression to evaluate and return. The value of that is going to be returned as the result of the entire ternary expression, if and only if the condition is true. The expression to the right-hand side of the colon is called the else expression. It is the expression to evaluate and return if and only if the condition is false. Are we doing okay so far with the concept of a ternary expression? Okay. So if you cannot remember exactly how it works, you can just look it up, okay? But when you do look it up, make it specific to C++ because Python has a different way of expressing a ternary expression, and the ordering of things is different in Python. So if you're already familiar with Python, you have to kind of change the order a little bit, because that's just how the languages work out. All right, very good. Okay, so now I'm once again erasing the examples here because I don't need those anymore. Cool. I have just expressed the two functions that I need in order to figure out how to compute the q, the k, and also the s digits. The x and y are given to you. Okay, in any addition, you are always given, okay, what two numbers do you want me to add? So x and y are provided. So now we just have to figure out, okay, what about q of I? In other words, I don't even care which digit we're talking about. The I is just a placeholder to of the digit itself. So how do we compute Q of I? So we look at this 9 here. Okay, this 9 is 2 plus 7. Okay, this 4 is the single digit sum of 6 plus 8. So given the way we have defined R and C, what do you use to compute Q of I? We use R. Okay, very good. So that's a really good starting point. So we use R. And what do we give R to compute Q of I? X of I and then Y of I. Okay. So we have to be very specific about the digit that is being used because one of these things is a little bit mm, tricky. What about S of I? So we are talking about this digit being 9, the single digit sum of 9 plus 1. This single digit here is the single digit sum of 4 plus 0. So what about S of I? How do we compute S of I? Okay, so we use Qi, Ki, and this is the single digit sum between those two. So it's the R between the Q of I and the K of I. I is representing the digit. So in our example, I would range from 0 to 2. All right. So now we only got one more to go, which is the K. The K is a little bit tricky because we compute the K of the next column. So when we try to define the K term, we say, okay, K of I plus 1. Okay, so the column that we are focusing on, not that one, is the one to its left. Okay, we're trying to figure out the K digit to the left of the column that we want to refer to. So what do you think is needed for that computation? All right, so we'll go ahead and specify C of xi, yi, C of qi, ki. But what do we put in between? In other words, if I were to put an operator here, what should I put? Okay, we for now I'm going to put a plus here. Okay, we'll just say, okay, it looks like it's just a sum between those two, and for whatever reason, the example only has the overall carry of 1 and never 2, but we don't know why. We'll explain that later. Okay, is that okay? Just using a plus? Okay, all right. So now we have defined how digits relate to each other. Given x and y, we can always compute the q, the s, and also the k. Is that okay? So this is kind of important. So if I was learning this like 30 years ago, actually 40 plus years ago when I was in college, I would have put this on one particular page of my notes because these are definitions. And I'd like to put all the definitions in one place so they're easy to find and I can look at the relationships between the definitions. So that's what I would have done. Okay, cool. So now I'm going to throw a wrench into this entire thing and ask, what about base 7? What if I want to teach the octopi in the world of SpongeBob how to perform multi-digit addition in base 7? What do I do? The tens, both tens, because we have two tens here. So we have one 10 over here, we have another 10 over here. So if we switch these to 7, then we would have specified all the rules for base 7 multi-digit addition. but Tag, what about the other stuff? What about how we compute Q of I, S of I, and K of I plus one? The relationship between the digits does not change. We only have to change the single digit sum, the way it's computed, and also how the carry is computed. Are we doing okay so far? Is everybody convinced? Say no. No. Okay, I heard no. Okay. Okay, since you're not convinced, I'm going to give you some examples. Okay, so let's go ahead and do some base 7 addition, multi-digit addition, and 3-digit stuff too. So let's start with a 2, 1, 5 plus we'll stick a 4 here and a 3 here. Which digit have I not used? No, you cannot have 9 because it's base 7. You can only go from, okay, let's stick a 6 here. Okay, cool. All right, multi-digit addition, but this is base 7. So we got X, we got Y, we got Q, we got K, we got S. Same kind of structure, okay? So we can actually compute the entire Q row first because the Q row is really just the R function applied to X and Y. So what is R of 5 and 6 in base 7? 5 plus 6 is 11 to us. Mod 7 is 4. That's the remainder. Okay, cool. What about 1 plus 3? What is the single digit sum of 1 plus 3 in base 7? In other words, what is R of 1, 3 in base 7? It's just 4, okay, because 4 is not greater than or equal to 7. So 4 is just 4, okay, not a big deal. And this is just 6 because 6, once again, is not greater than or equal to 7. So 6 is just 6. Okay, cool, cool. All right, so now we move on to the K, okay? This is always a 0 because I did not do anything to the right-hand side. This is the least significant digit. So the carry to the least significant digit is always going to be a 0. Okay, that's not a big deal. So now we need to figure out this thing here. So what is C of 5, 6 in base 7? So now you have to kind of remember, this is why it is helpful to put all the definitions at one place, because now on your own notes, you can just go like, oh, okay, that's what it is like. So if I were to go back to the definition of the C function, which is here, but remember, we are now dealing with base 7, not base 10. So now we have to ask, okay, U is a 5, V is a 6, 5 plus 6 is 11. 11 is greater than or equal to 7 is true. So it's going to return a value of 1. Okay, so now if I switch back to the base 7 example, so we know like, okay, this is going to give me a carry of 1 already. 4 plus 0 will give me a carry of 0. This one plus this 0 is a 1, so we put that one over here. 1 plus 4, excuse me, 1 plus 3 is 4. 4 is greater than or equal to 7 is false. So this is going to be a 0, or the carry is a 0. This is also going to be 0. 0 plus 0 is going to be a 0. So 4 plus 1 is 5. The single digit sum of 5 is also just 5. The single digit sum of 4 plus 0 is just 4. Now we can move on to the last column. 2 plus 4 is a 6. And then 6 plus 0 is also just a 6. 2 plus 4 is not greater than or equal to 7. So it gives me a C function of 0, or the result of C function applied to 2 and 4 is going to be 0. It's going to be a 0 here as well. So 0 plus 0 is 0. So my overall carry is also going to be a 0. Okay? So the drunk octopi in SpongeBob's world is going to be pretty happy because now they know how to carry out multi-digit addition with one can of beer, holding one can of beer so they can stay drunk. Cool. Okay, so this is what I claim. Okay, I claim that in base 7, 215, don't say it as 215 because that implies it is in base 10 already. So we'll just say this is 215 in base 7 plus 436 in base 7 is 454 in base 7, according to this math. So what do you do in tax class when I make a claim? I claim, tax claims, that 215 in base 7 plus 436 in base 7 is 654 in base 7. So in my classes, what do you do when I make a claim? You question it. Exactly. You say, okay, prove it, right? Okay. So the way I'm going to prove this, or the way I'm going to double check this, which is not a formal proof, is not a direct one. The direct one is easy, okay? I just go through exactly the same math carefully. But guess what? If I have a conceptual mistake, I would have made the same mistake again. Okay, so that's not a really good way to double check things. So now you go like, okay, but how else are we gonna check this? Oh, we can do this with base conversion. In other words, I can convert 215 from base 7 to base 10, convert 436 from base 7 to base 10, add the base 10 number, which we are all super familiar with, get a result in base 10. Then convert the base 10 number back into base 7, and we should get 654 back. Now, is there off chance that I might have made a mistake here, and I might have made some really crazy mistake in the other process, and they end up to be the same? Yes, it is possible. Is it likely to happen? Not very likely. Okay, so it's a good way to double check things. It's also a good way to kind of reapply things that you have learned already, to kind of go like, oh, okay, I can now apply what I have learned about base conversion. Okay, so now we'll work with 215 in base 7 is 2 of 49 plus 1 of 7 plus 5 of 1. So that would be 98 plus 7 plus 5, which is 110 in base 10. So when you don't see a little subscript here or in parentheses, that means we're dealing with base 10 number. When you see a little subscript here, that means that is indicating the base that we are using. All right, so we'll work with 436 in a very similar fashion. So it's 4 times 49, which is 7 squared, plus 3 times 7, plus 6 times 1. So that turns out to be, I think that's 196 plus 21 plus 6. 217 plus 6. So I think this is 223. All right. I could have made a mistake, which is okay because then the end result is not going to work out. So now I add the two base 10 numbers, 110 and 223. Those two add up to 110 plus 223. Oh, that's an easy one. They add up to 333. Coincidental. I did not plan to have the digits to work out like this, but it does work out like this. Seems like, it seems like that's okay. So now we want to convert 333 from base 10 back to base 7. Okay. So yes. Oh, you are correct. Thank you. So 333 converted back to um, base 7. So there are a few ways to do it, but if you're new to this, it always helps to spell out the powers of 7 that will be involved. So we have 7 to the power of 2, 7 to the power of 1, and 7 to the power of 0. It really helps to kind of look at all the units that are available. So now the first thing is, okay, let's divide it by 49 first. Okay, so 335 divided by 49 is going to be 6, which will give you 294. Yes, I did mental math. I think some of you are faster than I am in terms of mental math because um, I'm a little older and my mind doesn't click that quickly anymore. So this is a 9. and that is a 3, I think. Okay, so it's 6 with a remainder of 39. So this 6 accounts for this 6 here. I got one digit checked already. So now we look at the 39 and we do the same thing. 39, but this time we divide it by 7, which is 7 to the power of 1. And that would be a 5 with a remainder of 4. So the 5 is this 5 here. 4 is the 4 over here. So everything checked out. So once again, could I have made a sequence of 3 key mistakes so that this actually works out, even though the original example was wrong to begin with? Yes, that can happen, but is it likely to happen? The chances is pretty low. Okay, so but this is one way to double check things. Okay, and I want to talk about this not only because um, it helped us to kind of practice base conversion, but also in terms of thinking. When you read something like from a textbook, doesn't matter what class it is always helpful to ask yourself the question of, okay, this is a claim. Can I validate this claim using what I have learned already? You are giving yourself additional assignments to get a better understanding of the material. So that's a way of studying that I've been using, without thinking about it. But now that I can think back, like what I did 40 plus years ago as a graduate, as a student, I go like, oh, okay, that's what I've been doing. Yes. Yep, that is true. Yes. So, okay, so to expand on what you said of, you're turning yourself into the authority of everything that you learn. Many times, certain people will look at this approach and say, why are you reinventing the wheel? Okay, because people have done this already. You just have to use the result. The answer to that question is it is important to understand the fundamentals. Okay, there's a huge difference between saying that, okay, I know this theorem is true in a certain math class, as opposed to I know how to prove that theorem using my own steps. I'm not just reading and regurgitating the steps from somebody else. I actually derive the steps because that is by itself an exercise to help you understand the material a little bit better. And I can also tell you that in terms of proofs, um, well, these days, computers can do it too. If you go to Mathematica or Wolfram Alpha, they can do certain proofs pretty quickly. Okay, but proving things is an exercise of your mind to basically do thinking, logical, step-by-step analysis, and problem solving. So doing that kind of stuff more often would actually help to strengthen your cognitive ability when you need to go find a job. Okay, you need to figure out what you can do that AI cannot do. Okay, and this is one way to help improve your chances of being able to beat AI when you are when you graduate. Is that okay? Cool. All right. So now we look at this whole thing and go like, but tech, it is absolutely impractical to talk about and use base 7. Nobody do that. Okay, you're correct. Okay, but this is an illustration. In other words, I go like, okay, now that we know how to do base 7 stuff, can we do base 2 stuff? What do we do when we want to convert everything to base 2? Exactly. We replace the 10 with a 2. If it works with awkward stuff like base 7, base 2 is like easy peasy. Okay, so we'll do that then. Okay, so I do want to make sure that you remember the definition of R and C in base 10, and just remember we just changed the 10 to a 2, then the R and the C will work with base 2 numbers. Okay, so now we look at base 2 specifically and go like, okay, so in base 2, u and v as single digits, what can they possibly be? What are the values that v can take on when v is a single digit in base 2? 0 and to the base minus 1, since it's base 2, is 1. Exactly. It is just 0 and 1. Oh, okay. So v can only be 0 and 1. But since u and v are independent, so that means when v is changing, you can say, oh, okay, I can just be 0 the entire time. And then v can go like, okay, I'm flipping back and forth. So now u can also be 1. Okay. In other words, when u is 0, v can be 0 or 1. When u is 1, v can also be 0 or 1, and therefore we have 4 possible cases. Are we doing okay so far with this? If some of you are saying, but isn't that the beginning of a truth table? Absolutely. Okay, because base 2 is binary. Binary is, in this class, is almost exactly the same as Boolean. Okay, because Boolean is true or false. All you have to do is to go like, so instead of saying true, I'll just say 1. Instead of saying false, I'll say 0. Oh, they're the same thing. Okay, so now we can go like, okay, well, what about C of U of and V? Well, let's see. 0 plus 0 is 0. 0 is greater than or equal to 2 is false. Okay. 0 plus 1 is 1. 1 is greater than or equal to 2 is false. 1 plus 0 is 1. 1 is greater than or equal to 2 is false. 1 plus 1 is 2. 2 is greater than or equal to 2 is true. Very good. All right. So with just the C function, we end up with a truth table. Does it remind you of a truth table that we have kind of touched on already? Ampersand, ampersand. Very good. Conjunction. Okay. So that means, wait, if they are the same, can I just redefine C of UV in base 2 as U ampersand ampersand V? The answer is yes. That's how we're going to do it. All right. What about R? R is a little bit more cumbersome, but we're going to deal with it. So 0 plus 0 is 0. 0 mod 2 is a 0. 0 plus 1 is 1. 1 mod 2 is a 1. 1 plus 0 is 1. 1 mod 2 is a 1. 1 plus 1 is 2. 2 mod 2 is a 0. So you look at this column for R of UV, and you go like, I don't think we have a C++ Boolean operator that can do this. You would be correct about it. Not a single operator can do it, but you can still express it using kind of like a clumsy expression. Okay, so the way the clumsy expression works is to say, okay, R of UV, when do we need this to be true? Well, we need it to be true when U is false and V is true. Okay, so you go like, okay, what about this? If I negate U first and then AND it with V, that would be true only when U is false and V is true. Does that make sense? Okay, so that takes care of this one over here. Then you go like, but there's the other one over here. Well, that one it is a 1 for this particular combination when U is true and V is false. So you can now go like, oh, okay, maybe I can use this expression to say that this is true if and only if U is true and V is false. So now we have one expression to take care of the first one. We have the other expression to take care of the other one. So we only have to say, okay, what goes between them? Using an or, very good. Okay, so we stick an or here. Then we have a way to express, how R of UV can be calculated, but only in base 2. Okay, these will never work in other bases, but in base 2, they do work out. Okay, Now, if you also know the exclusive OR operator, that makes things so much easier because that's how exclusive OR is defined. Okay, so R of UV in base 2 can also be expressed as just U exclusive OR with V. And if you have read the notes, exclusive OR can also use this particular symbol, which is a plus with a circle around it. So I'm just going to re-emphasize the importance of reading the notes because sometimes I may not, out of you know just being forgetful, mention something that is in the notes. But your exam is based on the material from the reading material as well as the lecture. So that means if reading the reading material is actually kind of important. All right, so are we, oops, sorry about that. So are we good with all this stuff here? What we have done, okay, compared to what we had before is, okay, let's look at each one, individually. We used to have addition and comparison when we try to compute the C function. Are we using any of those? Nope, just a single logical AND, okay? As to the R function, okay, we used to require addition and division because mod is really a division, which is really kind of ugly, okay? Now we don't have any one of those. Instead, we only have logical operators. Logical AND, logical NOT, logical and logical OR. What is the big deal? Why is this particular step important? Exactly. Okay. So in I think on last Tuesday, I actually remember the day. So far, I can still remember what day I talked about what. At some point, it's going to be a blur to me. On last Tuesday, we talked about, oh, okay, look, we can use 4 transistors and make a what gate again? NAND, okay, a negated AND gate, okay. And then people go like, yeah, but the truth table of a NAND gate is really awfully strange, and we don't have a NAND operator in C++. You are correct about that, but we also know that NAND is known as a universal gate, which means all the other gates can be made by a structure or hierarchy of NAND gates. And in the lab on last Thursday, what gates did you make? What is gate 1 from last Thursday? Two, uh, oh, this is a Monday, Wednesday class. Oh, okay. Time shift. Last Wednesday. So on last Wednesday, what gate did you make from the lab? Gate 1 is a NOT gate. Gate 2 was a AND gate. So we actually knew how to do this. Okay, we can say, oh, okay, give me transistors and I can now give you a NOT gate, an AND gate. Now we didn't quite do the OR gate, but I think based on the material in the module, you guys will go like, oh, okay, if it can be expressed as an expression, we can build a circuit to do the same thing. Okay, so yes, we can actually build a OR gate out of NAND gate. So that means, oh, okay, so we are almost there. Okay, I think we can almost make a circuit to perform addition. There's one thing left. Looking at the time. So there's only one thing left. The one thing that is left, okay, and it deserves its own page. So the only thing left is k of I plus 1 because it involves c of xi yi plus c of qi ki. Now, some of you said, oh, but you can use an or in place of the plus. Are you sure? Because 1 plus 1 is 2. 1 or 1 is just 1. So they are different. So if you say we can just use an or, then you have to prove to me that it cannot be both true. C of xi yi cannot be true at the same time when C of qi ki is a 1. Okay? So here we go. Okay, this is a pattern. I make the claim that they cannot both be ones. So now, with the claim, you need to ask, I'm not convinced. Tech, can you prove it? Well, better yet, you can ask yourself, can I prove it? Have I learned enough in this class to show that C of xiyi and C of qiki cannot be ones at the same time? So this is what we will call a two-part proof. The first part is to say, okay, so we'll just start with an assumption, okay? C of xiyi is a 1 to begin with in base 2. Okay, so all of this only works in base 2. What does that imply? In other words, I'm asking if C of xiyi is a given, it is a sufficient condition to conclude what? So let's think about the function or think about how C of xiyi is defined in base 2. It's a conjunction, right? So if the conjunction of xiyi is a 1, what can we conclude about xiyi themselves? They're both 1s. Very good. Okay, so we can imply now xi is a 1 and yi is also a 1. This is the mathematical symbol for and. Sometimes I just switch to the math symbols. Okay, if that is the case, can I make a conclusion about Q of I? In other words, how is Q of I defined? It's the R of xiyi, right? Okay, so we'll write it down. It's the R of xiyi, but in base 2, it can also be seen as, from the previous page, the exclusive OR between xiyi. Okay, so we kind of worked on this before. So it's the exclusive OR between xiyi. And since we already know xi has to be a 1, yi also has to be a 1. So that means your Q of I has to be, well, okay, Q of I is the R of 1, 1 in this case. You don't even need to use the Boolean version of R. You can use the old version of R. What is 1 plus 1, the whole thing, mod 2? 0. Exactly. So we know that this whole thing has to be a 0. Okay, well, if Q of I is a 0, what do we know about C of Qi Ki? This also has to be a 0 because C of Qi Ki is the conjunction between those two. If one side is a 0, the whole thing has to be a 0. All right, part 1 is done. Okay, part 1 only says that if C of xiyi is a 1, we conclude that C of qi has to be a 0. But does it imply the other way around? No, it actually does not. Okay, so now we have to go for part 2, which is, okay, now we flip the whole thing and we assume C of qi ki is a 1. What does that imply? Well, in this case, it only implies that qi exclusive OR with ki is a 1, which gives us two branches. So this gives us two branches. One branch is to say, well, in base 2, the only time this can happen is qi is a 1 and ki is a 0, or, okay, this is or here, qi is a 0 and ki is a 1. Okay, so from this assumption or what is given to you, I can now come to these two possible scenarios. So for each one of these scenarios, then we go like, okay, if qi is a 1, what can I conclude? Okay, I think I just made a mistake. Okay, I'm gonna use a bad word, but since it's on myself, I think it's okay. That's a stupid mistake. Okay, because I expanded C incorrectly. Okay, I own this one. This is not an or. What is it supposed to be? This is C. It's supposed to be an and. Okay, my mistake. Sorry. There we go. But since I have a really fragile ego, so I'm going to blame it on you guys and say, how come you guys didn't tell me that I made a mistake? Or better yet, this was a test to see if you guys understand the material. No, actually, I just honestly made a mistake. That's all. Yep. Go ahead. Yep. Yeah, but it's not. It's yeah, it is the wrong way to do it. Yes, exactly. You get the same destination, but it's the wrong way to get there. Okay, but I think this works, right? C of QIKI is a conjunction like this, but because this is a 1, this also has to be a 1. But in order for the result of a conjunction to be a 1, each side also has to be a 1, which concludes that Q of I has to be a 1. Now we can go back to the diversion. So now we have two ways to make Q of I 1. One is xi is a 1 and yi is a 0, and the other one is xi is a 0 and yi is a 1. Okay, so now we have to proceed with both because this is a or. So now we go like, okay, if this is the case, then C of xi yi, which is xi and yi, is a 0. Okay, that seems pretty obvious. The other one is, okay, this one has the same conclusion because at least one of xi and yi is a 0, so the conjunction is also going to be a 0. But when both of these are combined, okay, so when you look at both of these, it implies that C of xi yi has to be a 0. So what have we learned here with this entire chain of proof? If you tell me that C of qiki is known to be a 1, I can now make a conclusion that C of xiyi has to be a 0. So now we have proven in the math proof, these are the best three letters to write in the mathematical proof because it says you are done. Okay. So now we have just proven that they cannot both be ones because if one side is a 1, the other side has to be a 0. Okay. This is significant because this is the time when I can convince myself that, oh, we can use or instead of plus to combine the two carry functions. In other words, this plus here doesn't need to be a plus anymore. We can now say, oh, okay, in this specific example, because of the constraints of how Q of I is defined, I can now just use a logical or. Now, why is this step significant? Why is this conversion from a plus to or significant? Is because plus is what we are trying to figure out how to do with transistors. Okay, so if you say in order to implement addition, you need to know how to do addition, I go like, yeah, that's chicken and egg. We don't like chicken and egg problems in computer science. Recursion, by the way, is not a chicken and egg thing because there's a base case. Okay, so it's not the same thing. But if we know that the differentiating case, which is when both sides are ones, cannot possibly happen because of how Q of I is defined, then we go like, okay, cool. We have the last thing that we need to say everything can be done using logic gates. So that means this equipped us with everything that we need to know in order to create addition as a circuit. Yes, go ahead. Okay, it's hard for me to know which where you're pointing at. So I'll invite you to point to it, using the pen. It has retracted, so it would give me the pointer, but not okay. That's exclusive or. Yep, yep. hmm But that's not a plus. It's an exclusive or. So one exclusive or with one is a zero. True exclusive or with true is false. Yeah, we are using the truth table from the previous page. So if I go back to the previous page, this part here, that's exclusive or. So when you have true, exclusive or with true, the result of the exclusive or is false. Exclusive or can also be expanded like this, which will also give you a false when U and V are both true. Because when U is true, not true is going to be false. This conjunction will give you false. And if V is also true, then not V is going to be false. So this conjunction would also give you false. Then you end up with false or false, which is false, which explains this false over here. Yep. And if you think about the way you use the term exclusive or in just normal English, it will also imply that those two things cannot be true. In other words, okay, I'll give you an example. All of you will probably only remember the example and forget everything else that we talked about today, but this is also why I recorded the whole thing. If I say, okay, now this statement by itself may not be true, okay, so I'm just saying that if this statement is true, what can you conclude? If I say either Iraj or Tech is an excellent professor, okay, can both of them be excellent professors based on that statement? Exactly. So that's how we use exclusive or in normal, everyday English. When we use either or, that is exclusive. When we do not use the either, it's just regular or. In other words, if I say Iraj or Tech is an excellent professor, it means, yeah, they can both be excellent professors. Or it's only implying that at least one of them is an excellent professor, but they can both be excellent professors too. If I say Iraj and Tech are excellent professors, that means both of them have to be excellent. Why? Because I haven't used the computer, I've been using the tablet all along. So the computer decided to fall asleep. And I hope it doesn't affect the recording. Yep, yep, because I've been using the tablet all along and I forgot to kind of move things a little bit on the computer itself. So that fell asleep. And where is my screen? Yeah, at least during the class, or have it long enough to last a class like 80 minutes. I think currently it's set to like an hour. I mean, most of the time I touch something on the computer in an hour, even in a lecture. Today is one of those rare days where I just exclusively use my tablet to do all the teaching. But oh, by the way, what do you think? Is it working out okay or okay? All right, cool. And it's all getting recorded as well. So that means, you can go to the recording and just go like, this is what I like, cut it out, slap it onto your Google Doc, and then print it out as your notes. You know, I don't object taking shortcuts as long as taking the shortcut does not affect your accomplishment of some long-term objective. Okay, so that means you're just saving time. Okay, you're doing something more efficiently as opposed to I'm taking a shortcut that would actually impact the longer term goal that I have. That would not be advisable. It is not wrong per se. I try not to use the words right and wrong. It's just does it work for you or not? Okay, so You know, it's a little bit different, perspective. Most people think they're the same, but yeah, I don't think they're the same. All right, cool. Um, are we getting a? Well, we still have some time left. Let me see. Oh, we can go through a few examples. Okay, I think that would be super helpful. So let's go through some examples of binary addition. Okay, so everything is a 0 or 1. So we'll start with 1, 0, 1, 1 plus 0, 1, 0, 1. Oof, okay. This is all in base 2, so I'm going to specify this is all in base 2. This is X, this is Y, this is Q, this is K, this is S. Okay, all right, let's do this. So we are looking at the whole row of Q. It is just the exclusive OR of the XY value of the same column. So we have a 0 here, a 1 here, a 1 here, and also a 1 here. Because it is this 0 is the exclusive OR 1, 1. This is the one of, this one is because of the exclusive OR between this one and this particular 0, and so on. Okay. Now, if you cannot do the Boolean algebra thing or the Boolean expression thing as quickly as I can, don't worry, because I've been doing this for a long time. Okay, probably longer than some of you have been alive, because I have been a software engineer, kind of specializing to low-level stuff since 1990. So that's a long time ago. What is it? 35 years? Yep. All right. So k is a little bit different. 1 plus 1 gives me a carry of 1. This is assumed to be 0. And then 1 plus 0 has a carry of 0. 1 plus 1 has a carry of 1. Stick that 1 here. 0 plus 1 has a carry of 0. 1 plus 1 has a carry of 1. 1 plus 0 has a carry of 0. 1 plus 1 has a carry of 1. And then we compute the exclusive OR again, because the sum bits are the exclusive OR between the Q and the K bits. So we have 0, 0, which is a 0, 1, 1, also a 0, 1, 1, also a 0, 1, 1, also a 0. Okay, so now I look at this and I'm questioning myself. It's like, did I do this right? Because I actually did not know what the end is supposed to be when I was using the example, when I came up with the example. So now I have to double check. So the way I double check is the same as the base 7 example, except this time it's base 2 to base 10, base 2 to base 10, and then the sum of base 10 back to base 2. Okay, that's the way it's going to work. So 1011 is 8 plus 2 plus 1, which is 11. 0 plus 1, excuse me, 0101 in base 2 is a 4 plus a 1, which is a 5. 11 plus 5 is 16. And we go like, wait, tech, 16 and a 0? Obviously wrong. Wait. Remember, the sum is broken into two parts. One part is the fixed width digit that has to match the number of digits of x and y. The other part is the overall carry, which in this case is a 1. Then you go like, well, why is it 16? Because tell me, what is this k? This is k0, so this is k4. So what is a 1 of k4 representing in value? It is 1 times 2 to the power of 4, because that's the position. 2 to the power of 4 is 2 times 2, which is 4, times 2, which is 8, times 2, which is 16. So the entire value of 16 is represented by the overall carry of 1 in this case. So everything checked out. They all checked out. Are we doing okay so far? So you can see that, in my lectures, I really frequently reference back something that you just learned. Okay, and that makes it really important to make sure that you are cleared with all of the concepts and definitions from prior classes, because without doing that, and I make references back to things that we have learned already, it makes it kind of really hard to make all the connections. Of course, yeah, go ahead. Hmm? Okay, so the 8 is from this one here, because this one is representing we have 1 of 2 to the power of 3. So that's where the 8 is coming from. The 2 is coming from this one here, because it is 1 times 2 to the power of 1. And then this one, obviously, is coming from this one over here, because that's 1 times 1. It's 1 times 2 to the power of 0, because this entire column is column 0, or digit 0. All right. Are there any questions? Okay. Hmm? Go ahead. We have a few minutes for tangents. Hmm. Hmm. Okay, so it is. So the technique that I use to prove that is specific to binary because I was referencing your conjunction and disjunctions. But the general idea that you in any base you cannot have both of those to be ones, that is true as well. So we can kind of gently touch on that. Oh, you do? Okay. Yeah. So what's your name, sir? Lux. So what Lux is saying is the claim that C of xi yi cannot be a one when these two terms cannot be ones is actually true for any base. It's true in base 10, it's true in base 7, it's true in any base. And you have the proof to do to show that. Hmm. Yep. Yep. Hmm. Yep. So if I were to capture your idea, this way being one implies xi plus yi has to exceed whatever the base we're dealing with, right? Because that's the definition of the original C function. So um, so we have to come to the conclusion. So we have to relate this to oh, okay. So I see how we can do this. So this implies Q of I is going to be xi plus yi, the whole thing mod b. But in this case, x of I, um, basically we can look at this and say this has to be less than or equal to b minus 2 because xi can only go up to b minus 1, xy can only go up to b minus 1. So now you have 2b minus 2, and when you take the mod, uh, when you do the mod b with 2b minus 2, then it is at the most b minus 2, which means even if you're, so it also relies on k of I cannot exceed 1. So it is in a way self-referencing. Yeah, yeah, yeah. So right. But you can also use, okay, this is way out of the scope of this class. So if you guys have say, okay, I have no idea what you're talking about, you are, it's rightfully so. if you have not taken CISP 440. Because if you've taken CISP 440, you would have some exposure to the concept of proof by induction. And in proof by induction, we start with a particular base case, which in this case is K0 is known to be 0. That's our base case. Because without the base case, you cannot claim that the K bits cannot be a 2. Yep. Okay, but I get it. Yep. I know how to do this proof too. It's just that, the binary case is so much easier to deal with. Yep. All right. So that is about all the um, lecture material that I want to talk about regarding binary addition. Even though this is only 80 minutes, there's a lot of stuff. Okay. The difficulty of this particular subject or the way that it is presented is because there's a lot of symbols involved, a lot of definitions, a lot of symbols, and I progressed from a concrete base 10 case to the structure, and then I look at the structure and go like, can we do this with other bases? Yes. And then I use base 7, then I switch to base 2. But base 2 is a special case because when you look at all the possible cases, they can all be implemented using Boolean operators. And then the last bit was to do this, kind of analysis to say that, the two C functions cannot both return 1, and therefore the last addition can also be converted into a OR, and therefore now everything can be done using logic gates. So that's kind of like the high level map of what we did today, which can be important because sometimes when we are stuck with a lot of pine needles, we don't know where are the trees and what does the forest look like. So sometimes it's important to take a step back and go like, okay, where are these pine needles coming from? Okay, and I think it's really important, okay, because the technical stuff, the math of it is really important. I feel that is important, but it's also important to understand so what, right? Well, the big so what of today's lecture is now we can start to construct addition circuits because we know how to do and or not gates, and everything is now expressed as and or not. We know the structure of how to derive the Q, we know the structure of how to derive the K, and we know the structure of how to derive the S given the X and the Y. So it's just a matter of, oh, so how do we structure these gates in order to perform the actual addition, which we'll kind of talk about in the next class. Which is next Monday. I have to remember today is not a Tuesday, Thursday. So next Monday, we'll start to look into the structure of those things. And also to answer the question of, but what about subtraction? Okay, it is cool that we can do addition, but what about subtraction? Because subtraction is hard, it has got borrow and stuff like that. Follow exactly the same steps. Okay, base 10, generalize to a structure, define the functions, relate the digits together, and then abstract the method to say, oh, we can use this method with any base, including base 2. Look at base 2 as a special case, look at all the functions and go like, oh, in base 2, we can convert this into this Boolean expression, and this become that Boolean expression. Done. So it's going to be following the same structure with binary subtraction. And once everything is done, you guys would go like, oh, I did not know that subtraction is that close to addition when it is really the case. It's really, really similar in many, many ways. So that's the preview of subtraction. But today we still got a lab to do, and the lab is going back to just base conversion. And I still haven't gotten time today, this morning, to change the due date and stuff like that. But this is what you'll be doing today. It is still open book and open notes, so you guys can go ahead and, oh, I'm gonna write down the access code first, which is heptapod, heptapod, and then we turn on the GP filter. Today is September 3rd. And this is due at 1:20 p.m. You can start now. All right, save and publish. So now you should be able to see the base conversion lab activity. It does not involve the use of Logisim, so some of you may feel a little bit of a relief, and others, maybe a little bit of disappointment. It does not need um, Logisim. You can use the GPT TA to help you with these things too, if you want to. Um, but but that's the homework assignment. That's the lab for now. It's just about base conversion. All right. The access code is heptapod, which describes beings that have 7 limbs, like the aliens in Arrival. Right. Well, I'm gonna go get some water to drink because I've been teaching since 9 o'clock and haven't got a chance to get a drink. So I'm gonna go get some water and I'll be back. And I can turn off the recorder now.